So, hello everybody. I'm very happy to host Jean Honorio here. Jean is an assistant professor in the computer science department of Purdue University, as well as in statistics department. Prior to joining Purdue, Jean was a postdoctoral assistant at MIT, working with Tommy Giacola. His largest number is 3. His work has been partially funded by NSF. He is an editorial board reviewer of JMLR and has served as area chair of NURI IPS, senior PC member of IJCAI and AAAI, PC member of NURI IPS, ICML, AI Stats, among other conferences and journals. So I'm very, very excited to host Jean here. Who will give us a talk about theoretical foundations of combinatorial problems in AI. So Jean, the stage is yours.
Oh, thank you. Yeah, so thank you for letting me give a talk. And I always like to start with who have been my students and who are currently my students right now at Purdue. The first one is Ashish Ghoshal. He graduated a couple of years ago. Right now he's at Facebook. Kevin Bayo, he just graduated on the summer. I forgot to update the slides. So Kevin Bayo is now doing a postdoc in UChicago/CMU type of opportunity, mainly based on UChicago. And my two current students are now Adarsh Barik and Shuyan Ke. The one that I will be talking, the work that I will be talking more about is the work actually from Adarsh Barik, which just was recently accepted as a spotlight at NeurIPS this year. And I like to work with the students in general. Every year I usually teach what I call the hands-on learning theory seminar every fall semester, and that has allowed me to collaborate with several students through the years and publish a lot of papers. And I guess the count is so far around 24 since the beginning as an assistant professor, but currently 13 students are still at Purdue, but the total count is, I believe, around 24 or so more students through the seminar. And I have to confess, I like to start also saying that I have to confess that I might be one of the persons that don't know how to pronounce his own name, actually, because although I am from Peru originally, my name is French, so it should be something like Jean, but I will not pretend to say it properly. If there is anybody from France in the audience, please excuse me, because I will not be able to pronounce my name properly, as one of my French friends told me a long time ago. So let me try to give you an idea of a framework that we have been working on through the several years. So several problems in machine learning and artificial intelligence are combinatorial in nature. And as we all know, most of them are NP-hard problems in the worst case. And the goals that my particular research group has is to generate algorithms that are correct. And that definition of correctness will become a little bit more clear in the next slide. So we want algorithms that return the true solution of a problem. Then we also want algorithms that are computationally efficient, if possible, polynomial time. We also want algorithms that don't require too much data. Therefore, it should be statistically efficient. Making all these, the algorithms, making them suitable for the high-dimensional type of problems. And the framework that we have been working with is the idea of applying some type of continuous relaxation to the original combinatorial problem, and then using prime dual certificates. I will use later one particular problem because continuous relaxations have been used for a long time, and but there is some difference in the way we are applying these continuous relaxations in the different works that we have been doing. Take, for instance, one of the problems that I will be talking more about is this problem of fairness and the biasing as an excuse to show the whole framework. Consider this problem in which you want to do regression, but let's say you have two groups of samples. And this problem happens a lot when one considers, for instance, imagine salaries, right? And then you have two groups maybe divided by gender or religion or many other possible attributes. And then imagine, let's say we have a group that we will have the group 1, and then we have another group that we will call -1. Let's say the expected value of the response variable, let's say could be salary when you do the regression from the vector x to the scalar value y. Let's say in the group 1, the expected value of this response variable is gamma. And let's say in the group -1, the expected value of the response variable is minus gamma. Then you can see, for instance, in the way to think about this in the case of fairness is the case of disparities in terms of salaries between different groups. Now, to make the problem a little bit more complicated, let's assume that we don't know the assignment of the samples to the two groups that we have at hand, right? So then we will have to do some sort of clustering at the same time we are doing the regression. We are trying to solve the regression problem. And this is the motivation for this is that sometimes the disparities between two groups are not necessarily explained by things that we directly observe in a feature. Sometimes the disparities between two groups can depend on many more features like education level and many other things like gender, religion, and many other things together. And you would like to have an algorithm that also tries to figure out what are the factors that are defining the disparities between two different groups. So we call this kind of a regression plus clustering problem. So we're trying to solve both things at the same time. Now, what can be this useful for? So one possible use of this is to do some sort of debiasing. So the idea is that if I was able to cluster the samples in the two groups and at the same time do the regression, then if I know that the samples fell into the group 1, where the expected value is gamma, I can subtract gamma from that group. And for all the samples that fell into the group that is labeled -1, I can add the value of gamma for the second group, and then the expected value in both groups will be 0. And that would enforce a fairness notion that is known in the literature as the equal means fairness notion. But of course, for that, we need to cluster the samples. Right, so then something I want to say is that for this particular work, we are assuming that we know the value of gamma. Later in the experiments, for the theoretical work, we assume we know the value of gamma. Later for the experiments, I will show that the value of gamma doesn't have to be known exactly. So some rough idea of what is the value of gamma will be enough for experimentally speaking. But for the theory, we need to know the value of gamma, and it will become a little bit more evident later. So this is the idea of the problem. So we have some attributes X. Imagine we have n samples, and we have D features. So we have this matrix of the inputs, and then we have a vector of the responses for one scalar for each of the n samples. Our idea is the goal is to recover a sparse parameter W. So this W will be the regression vector that is D-dimensional. We will try to find a vector that has a lot of zeros as entries in the vector, and then some few non-zero values. That's what we call it sparse. And then we will also try to recover the hidden attributes, meaning that for each of the sample, we will try to figure out whether that sample is in the +1 group or in the -1 group. And so our goal is to recover those two things, the regression vector and the cluster for each of the samples. So seeing just as a pictorial representation, we have as an input X and Y. We run this through our regression clustering algorithm, and we try to recover the vector W and the vector Z. So let's try to see how does this look like as an optimization problem. So the way to model this as an optimization problem with the conditions that I mentioned before would be to minimize first part, that is the mean square error. And here you can see that the typical mean square error happens if I didn't have this gamma parameter that is this gamma value that is a scalar and this z vector that is +1 -1. If you remove that gamma times c from the first part, then you would have the typical mean square error. But here we have this extra label for each sample, and that gives us a plus gamma or a minus gamma depending on the label of the sample. So the first one is a mean square error. The second part is because we want to recover a sparse vector, so we add this penalty in the L1 norm of the vector, and this small lambda here is the regularization parameter that we need to set. The theory will allow us to set it properly. Now, also, we minimize this with respect to W and C. And remember that Zi, each of the entries in that vector, has to be either +1 or -1. So let's put as a Ci squared equal to 1. There are many extensions for this problem. For instance, that I will not get into the details, but imagine you also have a constraint that you want to have the same number of -1s to the same number of -1s as the +1s. So what I could do is to add these constraints where I multiply as an inner product the vector C with a vector of all ones, and if that is equal to 0, I am balancing the same number of +1s and -1s there. I could also add other things in the objective function. For instance, imagine I give you a list of samples that should match in the label. So if you have -1, the other sample should be -1. If it is +1, the other sample should be +1. Then if that's the case, you can add this extra part that does the, if for every ij in the list that should match, you can multiply Cij and put it in the negative, because remember we are minimizing here, so that will encourage the sample I and sample j to have the same sign. And if you have a list of things that don't match, you can also minimize the multiplication of Cij for every pair of samples that are in the don't match list. So if you add the second type of extra terms in the objective function, you can make this problem even more complicated. So it will end up being something like a max cat type of problem. But I will not get into those details. My goal in the presentation is to go to this initial simple problem. What I want to mention is that this problem in its simple form is already NP-hard. So it can become a little more, even more complicated if we add extra things. This problem is NP-hard by the reduction to the quadratic, the mixed quadratic programming, right? So a quadratic programming that has scalars as well as integers. That's the type of problem that we have here, and that problem is NP-hard, and we have those details in the paper. Now, of course, let's try to model this in a different way, and in order to make the notation a little simpler, I will introduce here a matrix that I will call MW. So this MW is a n+1 times n+1 size matrix. And the first row, first column entry of that matrix, M of W, is precisely the mean square error without the Z part. But then you can also see the n-dimensional vector, which will be this part, the xw minus y part. The transpose of that is here. And then we have some identity matrix, n times n identity matrix there. If you consider the match, don't match type of extra terms in the objective function, this is where you would put it wherever the identity matrix is here. And then you would have a problem that is a little more complicated, as I said, relating to the max cut. But this is the kind of things that you are encoding in this M of W matrix. And now I will be using in the next slides M of W just to remove the unnecessary complexity of the main points that I will be doing here. The idea is that this problem that I'm showing you here is exactly the same problem that I was showing before, but I am using a little bit of matrix notation. So for instance, here I'm using inner product between matrices, meaning that you will multiply the corresponding entries between the two matrices and sum across, similar as you would do with vectors. Here I'm using the a rank 1 matrix where I'm taking the vector z, that is an n-dimensional vector. I'm adding an extra one. I'm multiplying that with a transpose of the same vector. So this is precisely the same as the previous mean square error that I had in the previous slide. The zi square equal 1, I can encode it in this way. I can take the rank 1 matrix that you can see here, the 1z transpose. And if you think about it, the diagonal of that matrix is the first entry is 1, the second entry is c1 squared, then c2 squared, and so on and so forth. So this constraint, where the diagonal of this matrix is equal to a vector of 1s, is encoding the same constraint that I had in the previous slide. But there is a reason why I'm doing that, because this problem is still non-convex, but one of the typical things that we do in order to get some convex optimization problems in several other problems is to replace these rank 1 matrices with a matrix, let's say capital Z. So because this rank 1 matrix, we know it is positive semi-definite. Therefore, let's say, what if I replace that rank 1 matrix with a capital Z matrix? And this is an n+1 times n+1 matrix. So whatever the rank 1 matrix was in the previous slide, I am putting here a capital C. The diagonal of that capital C is a vector of 1s. And that capital Z matrix is positive semi-definite because the rank 1 is positive semi-definite. In other problems, whenever we do that, we end up having a convex optimization problem, but not in this one. So this problem is still a non-convex optimization problem. It has quite interesting structure though. So if you fix the W vector in this problem, so imagine you make a W vector constant, then this problem is a semi-definite program, which is a convex optimization problem. And if you fix the matrix Z, this problem is nothing else than the compressed sensing problem, the sparse linear regression problem. So it is convex when you fix one parameter and you think about the other parameter, but it's non-convex in the two parameters at the same time. For some time, initially, I thought that this problem was a convex optimization problem, but then we show also in the paper that the problem is indeed non-convex. So let me give you a small definition, because the fact that this problem is non-convex doesn't mean that nothing will work. Let me define this concept of invexity. So we say that a function phi is eta invex. So I am qualifying the invexity definition by this function eta. So this function phi is eta invex if and only if phi evaluated at 2 points, u minus the evaluation of the function at b, is greater than or equal than the gradient of this function at a point v times a vector function, a function that will output a vector, and that function receives two parameters, the point u and the point v. And this has to be true for all points u and v in the space. If you have seen that definition, you will notice that this definition is very similar to the definition of convexity. So a convex function is actually eta invex when we make the eta u comma v equal to u minus v, just the difference between the 2 points. If you plug that eta function there, that is precisely the definition of convex functions. So this definition is quite interesting, and I will explain a little more later. What I want to say for now is that the optimization problem that I showed you before, although it's non-convex, it is invex, okay? So that's the same optimization problem, but here you might be asking, what is the eta function that relates to that particular problem? And of course, we need 2 points, right? So here the variables are w and z together. So I need w and z is the first point, and then w bar z bar is the second point. And the definition of the eta function goes for, we need to output two things, something in the W space and something on the Z space. So in the W space, we just follow what the convex functions do, which is W minus W bar, the difference between the first part of the 2 points. But in the Z space, we need to do something a little bit different. So instead of just outputting C minus Z bar, which would be the typical thing for convex functions, we need to pre-multiply that by MW plus identity. Remember that M is this function that outputs a matrix given some particular W. So we need to pre-multiply that by MW plus identity, and also with the MW val plus identity inverse. For that particular eta function, you can show that this optimization problem is indeed eta invex. So what are the possible benefits of that? I will try to explain it in few seconds. Now, you might be asking, well, I was talking about worst case NP-hard problems, and at the same time, I'm talking about efficient, computationally efficient algorithms, right? In some cases, one can get polynomial time algorithms, and then you might be thinking to yourselves, well, if you have a worst case NP-hard problem and you're telling me that sometimes you can solve that with a polynomial time algorithm, why you didn't get the Clay Math Institute prize, because we know that we haven't solved the P versus NP problem, right? So here is the trick. So the difference is that we are not claiming that these problems are not worst case NP hard. They are, of course, worst case NP hard, but we are making an assumption on how the input to these problems is generated. So we are leaning towards more cases of average case complexity or a smooth complexity, right? So let me give you an idea of how these extra conditions work. So what we will do is we will assume that there is a true sparse parameter vector, W star, that is a d-dimensional vector that has a lot of zeros and few non-zeros. And we also assume that there is a true setting of the two clusters +1, -1 for all the samples. So there is a true W star that is d-dimensional. There is a true C star that is n-dimensional +1, -1 vector. Then attributes are generated randomly. So this matrix capital X that has n samples and d features, that is generated randomly. And also we will generate some independent noise for each of the samples. And this is the vector E that is n-dimensional. Now, we will give some sort of signal so that the algorithm can guess what is the correct answer. And the signal comes in this flavor. The response Y will be equal to X times W star, the true parameter, plus gamma times C star, the true assignment of the sample to its cluster, plus the noise E. If you remove the inner part, the gamma times C star, what you have is the model that people have been using for a long time in the compressed sensing kind of a scenario in the sparse regression literature. We are adding this extra gamma C star in the model. So now pictorially, this looks like this, right? So there is a true parameter W star and C star assignment of the samples to clusters. There is a generative model that will give us the matrix X and the vector Y. And then we only receive the matrix X and the vector Y, and we apply our regression plus clustering algorithm, the optimization problem that I showed you before, and we have to guess a W vector that will have some similar properties to the W star vector, and we will try to guess the assignment of the samples to the clusters, which has to be equal to the original Z star that generated the data. So this is the type of guarantees that I will claim. So let's first let me define the notation. So we define the support S of the vector W as the entries that are non-zero, right? So then if you give me a vector W, I look at every entry Wi of the vector. If that entry is different than 0, then that's an integer that gets into the set S of W, and that is the support of the vector W. So what we claim is that this index optimization problem that I was showing you before will output the true solution, meaning that's the correct solution, because the support of the W that I will output will be equal to the support of the W star that generated the data. And the Z matrix that will output will be equal to a matrix that I will call capital Z star, and is nothing else than the 1 followed by C star. Remember that C star is a n-dimensional binary vector with +1s and -1s. So this will output the rank 1 matrix, meaning that you will be able to get the labels of all the samples just by inspection of this capital C star matrix. And that will happen with high probability, provided that you have enough samples. The number of samples that you need to have is logarithmic in the dimension of the vector W, and also depends polynomially in the size of the true support. Right now we have the size of the support S to the power 3. I believe we can actually make it to the power 2 without adding too many assumptions. We're still not 100% sure how to do it, but going to the size of S log D will be a lot harder. So I believe with some extra tricks we can get the size of S squared, but the size of S will be a little bit more tricky to get with a lot of extra assumptions and keeping an algorithm that is still efficient. Now, the other thing that I want to say here is that notice that this part here, we are saying that the matrix that this algorithm will return is precisely the rank 1 matrix of +1s, -1s, and we are not applying any any sort of rounding of the solution, and we are not claiming bounds in like the duality gaps or anything like that. We are claiming that the solution is precisely what we wanted to have, so we are exactly recovering the solution that we are expecting. And that type of results are actually very different from the use of convex relaxations or invex relaxations in this case that you might find in the theoretical CS literature, for instance, right? And I want to claim also that this is the first time somebody have used this type of techniques for invex problems, the primal dual type of technique that I will show you in a few seconds. So, and please feel free to ask any question at any point of the talk. What I will do here is I will give you some history about this and a little bit of insights of how do we get these results without getting into too many details.
I have a question, if it's okay.
Sure, please.
What exactly is your assumption about the distribution of X? Like, do you assume that every entry in the matrix is an independent random variable, and do you assume something about the distribution?
Yes, so what we are, I think in this first version, what we are assuming is very similar to the compressed sensing type of literature. The entries or the vectors of each sample is a sub-Gaussian vectors that will fulfill the mutual incoherence type of conditions.
Okay.
So there is not much effect between the features that are outside the support with respect to the features that are inside the support. And so let me give you some little story. Oh, hi. Yes.
Can I ask another question?
Oh, yes, please go ahead.
So you mentioned at the start of the lecture that it is NP hard before the relaxation. So after the relaxation, that's not hard, or it's not hard only to approximate? Or you're not even guaranteeing a non-exponential time?
Yeah, so after the relaxation, you get an invex optimization problem, and I will explain actually to give you some intuition about that, about the invexity, but the type of conditions are very similar to what you get in convex optimization problems. So it's possible to get some algorithms that are actually very efficient. And the type of algorithms that one can apply here is a type of a gradient descent type of algorithms, and they will work. But I will complete the answer in a couple of slides later to give you a complete answer to your question.
Thank you.
Yeah. So this, I will talk about this primal dual witness. I will concentrate on that today. And this type of methods that will use these Karush-Tucker conditions in the optimization problem have been used already a little bit in the past. So there is already some history of these techniques being used in the sparse linear regression type of literature. The first one that started all this idea of the generative model and trying to guess the original parameters that created the data at hand was the famous mathematician Terence Tao. So that's the Tao that you see in the 2005 paper. But then Ruderson and Verschining, Martin Wainwright as well, worked in sparse linear regression. In the literature of low-rank matrix completion, there is also work by Candes and Plan, and in community detection by Abe, Bandeira, and Hall. So they have been using this type of primal dual witness that I will explain a little bit in a few seconds from now. To answer the second question that it was, and I will come back to the random variables also at some point to that question. So to the second question, the reason why I was talking about Invexity, and this was kind of a learning experience for me as well, was that Karush-Tucker conditions, as we know, those conditions are necessary even for non-convex problems, okay? But those conditions are sufficient for Invex problems. And that was shown by Hanson in 1981. I confess that before getting into this research, I actually thought that held only for convex problems. I thought that for convex problems, Karush-Tucker conditions were if and only if, right? So what is the good thing about now Karush-Tucker conditions being necessary and sufficient for Invex problems is that I don't have to pay attention if I want to give guarantees about exact recovery or guarantees of how good my algorithm will work or my optimization problem will work. Karush-Tucker conditions, since they happen if and only if, they are characterizing the optimal solution of this optimization problem. So I can avoid getting into the dynamics of the algorithm that I will use for this for solving this particular optimization problem. I know that the optimal solution will fulfill if and only if the Karush-Tucker condition. So that will be a nice mathematical representation of the optimality of a solution. Second, and also very interestingly, a function is Invex if and only if stationary points are global minima, right? So I have to confess that I thought that would happen only for convex functions, but that's actually what happens for Invex functions. And that was shown by Ben Israel and Mond in 1986. So these two things are quite interesting. So that motivates what I will discuss in the next slides. So this is the same optimization problem in the top, what I was showing you, the MW inner product with the matrix C. So this is the element by element multiplication and summing over. I have the L1 regularization and the constraint that the diagonal of the capital C matrix has to be all ones, a vector of ones, and the Z matrix has to be positive semi-definite. I will say that here, when I use diag with a small d, that means that I take a matrix and I output the vector containing the diagonal elements of the matrix. When I use diag with a capital D, my input will be a vector, and I output a matrix where the diagonal is that vector and it's 0 in the off diagonal. So, well, one thing we do typically for this in optimization, if you're familiar, we'll first write the Lagrangian, right? So we have the objective function. This first part is nothing else than the objective function. And then we add our Lagrange multiplier. So I will need, for instance, for the diagonal z equal 1, I will need a Lagrange multiplier that I will call vector nu. And these two terms are taking into account the first constraint that I have here. I just rewrote it with the diagonal v because I can put the diagonal on z, or in the v, I just rewrote it for easiness of the next derivations that I will do. And then I do have the positive semi-definiteness constraint, which in canonical form, it should be minus C less than or equal than 0, or negative semi-definite, and that is why you have a negative here. And this extra capital lambda matrix, not to be confused with this lambda matrix, that also has to be positive semi-definite. So that's related to the dual feasibility. So now if I list all the Karushka-Tucker conditions, you end up having this. You have the constraints of the primal problem that I showed you here. So this is the primal feasibility. Then we have the stationarity condition, meaning that I take the L, take the derivative equals 0. So we can take the derivative, let's say, first with respect to the Z. So if you think about here with respect to Z, you have this term that is linear in Z. Then you have this second term and the last term. So you can see here from the terms that have the Z, MW plus the diagonal of V minus capital lambda has to be 0. So if I rearrange that, capital lambda is equal to MW plus diagonal mu. Then I have to do stationarity with respect to the vector W. So I do have, for instance, here a first part, which is differentiable, and I can take the gradient of this with respect to the W vector, which I have written here. But then here I have something that is non-differentiable. So in order to do that, I will call the subgradient of this L1 norm, I will call it G. So then this is this gradient of this part plus gamma G has to be 0. And if I rearrange that a little bit, you will notice that I can get G is equal to -1 over lambda, that gradient part. But of course, G has to be an element in the subdifferential set of the non-differentiable function L1 norm of W. Then the other Karushka-Tucker condition will be complementary slackness, which means that the inner product, element by element multiplication and then summation, has to be equal to 0. The good news here is that both matrices are positive semi-definite, and that's the dual feasibility of the Lagrange multiplier that I add here. The gamma has to be positive semi-definite, and C is also positive semi-definite. Then the inner product of this being a scalar 0 means that the multiplication of the two matrices has to be a matrix of zeros. One direction is easy to show. The opposite direction is shown by contradiction, but this is a fact. When the two are positive semi-definite, then if and only if the second thing happens. But then you notice in these equations, there is something that we can simplify, because here I'm already telling you what is the value of capital lambda. So I can just plug this capital lambda here. And of course, I can just plug the capital lambda here and remove one variable, one dual variable from the whole system. So let me do that, and I will simplify all these equations. So here you can see the equations, and you can see that capital lambda is there no more, because this is the lambda C equal matrix of zeros. This is lambda positive semi-definite. Now, my goal will be this. What I will try to do is I will construct variables in the primal problem, and so primal variables and dual variables. So I will construct a vector W and a vector Z that will, and the dual variables mu, that will fulfill all the conditions that I am showing you here. And if I am able to do that, I have an optimal solution, okay? So I will construct a W such that the support is equal to the support of W star. I will construct a Z, and I will make the Z equal to that value that I want, the 1C star, 1C star transpose. And this is a little bit of hindsight information. It will become clear why I'm setting mu equal to that particular value. So let me go one by one, and I promise you this is pretty quick. In the next 4 slides or so, we will do this. So the first one, in primal feasibility, diagonal of Z is equal to vector of 1. C is positive semi-definite. If I plug C equal to C star to this matrix, rank 1 matrix that I have here, then you will notice that C star has +1s and -1s. And here I have 1, C1 star squared, C2 star squared. That diagonal of that matrix is vector of 1s. And of course, that rank 1 matrix is positive semi-definite. So I am good so far. I am getting what I want. So let's go for the second condition. So the second is a little bit more complicated. This is stationarity and dual feasibility. So here we have G equal to this gradient. And what I will do, I will start making the vector W equal to a lot of zeros where I know where the zeros are. Here it looks like, just for simplicity, it's not necessarily consecutive, the zeros. I'm just doing this for simplicity. I will set a lot of zeros where I know where the zeros are, and I will have a vector u that is the same size of the support. And then later I will tell you how do I set that the non-zeros in that vector. So first, we need to understand a little bit about how the subgrading of the L1 norm looks like. And this is very similar to what people do in compressed sensing. So the idea, if you think about the subgrading of the L1 norm, remember G is a vector, so it will look like this. So if I is in the support, meaning if Wi is different than 0, then the absolute value of Gi, the corresponding entry in the vector G, will be equal to 1. In fact, if Wi is greater than 0, Gi has to be equal to 1. If Wi is less than 0, then Gi has to be equal to -1. So it will mirror the sign of the Wi entry here. Now, if you look at the other side, if I is not in the support, so if Wi is equal to 0, you can set Gi freely from anywhere between -1 and +1. So the absolute value is less than or equal than 1. So that creates some issue, because if you just give me the value of Gi, I will never tell you whether that corresponding entry Wi is non-zero or 0. So the trick that people use in the compressed sensing literature is to make one of the two conditions strict. So what we will do is we will make the magnitude of Gi strictly less than 1 when Wi is equal to 0, so that I have a way to now think about the two conditions. If the magnitude of Gi is strictly less than 1, I will know that Wi is exactly equal to 0, because if it is equal to 1, if the magnitude is 1, I would say that Wi is different than 0. So that will be our first condition that we will use. We will say that the maximum magnitude of any Gi for I not in the true support, not in the support of W star, we will make that strictly less than 1. And we know how the G vector looks like. We know that the Gi vector will be the ith entry of this thing. So now let's plug in the C star that I already told you before, the 1 C star transpose. So I will take the ith entry of that and the magnitude. The reason why I'm highlighting that in orange is because the random variables play into there. So I will have to, this expression of the gradient will depend on X and the matrix X and the vector E of the noises that I add. And this thing in orange is something that I will have to show by concentration inequality. So now the framework is giving you some condition that you have to show what is the probability of that conditioning happening. If that condition happens, then I will be able to figure out the zeros where they should be in the solution that I am that the optimization problem is providing. But now I talked about the zeros in the vector W that I output, but I also need to talk about the non-zeros in that vector. So now remember, U is the vector of the size of the support. The one way we can set it is, if we already figured out all the zeros, we can consider a small dimensional problem. So this problem just minimizes across the U that is size of the support. I am making 0 everywhere else. So my loss is very similar to what I had before. Instead of the L1 norm of W, I will use just the L1 norm of U, because I already know that everywhere else is zeros. But one of the things that will be important here is that I want to have a unique solution. I don't want to only have an optimal solution. I want something unique. A very simple way to enforce uniqueness here is to say that the first part, the differentiable part, will have a positive definite Hessian. So that will be the next condition that I would like to have for uniqueness. So the Hessian of that part of the loss, whenever I want to figure out the U vector, that has to be strictly positive definite. That I have to show also by concentration inequality. So this is the second condition that the framework gives us that we have to show. Again, that's for the uniqueness of the non-zero part of the vector W. So let me now go quickly with the next condition. We already tackled 1, 2, 3 kind of conditions. Now there is the next one, which is the stationarity and complementary slackness. And in this one, if you remember, we need to do the MW plus diagonal nu times Z, a matrix of zeros, okay? Now, let's assume that the whole first part here, the MW plus diagonal nu, let's call that A. Let's call that matrix A. And remember that I am setting Z equal to Z star, which is this rank 1 matrix. So this, all this thing is A. So this is here in my slide. The Z is what I am putting already here because that's what I want to get. So I'm setting that variable to that particular value. So what I'm claiming is that that matrix is a matrix of, that multiplication is a matrix of zeros, if and only if the vector 1 followed by the Z star, which has the n plus 1s minus 1s, that vector has to be the eigenvector associated to the 0 eigenvalue of A. This is a way to see it. So let me show you very quickly. So if a vector is eigenvector associated to the 0 eigenvalue of a matrix, then by just definition of eigenvalues, you would say that A times H is equal to 0 times H because 0 is the eigenvalue here. Then if I multiply by H transpose both sides, you would get H transpose equal to 0 H transpose, and that's a matrix of zeros, right? And that's exactly the shape that I have, here. So that's one nice thing. So we know something about this matrix now, the MW plus diagonal nu. We know that it has one eigenvalue that is equal to 0, and the eigenvector associated to that is the vector C star with an extra 1 there. The setting of the nu that I gave you here above is just to make that thing hold. So if I set nu here in the diagonal nu to this value, then you will get this expression, and just by linear algebra, you can convince yourself that you will get the matrix of zeros. So I'm setting the dual variables so that I get what I need. And that's what I meant by hindsight information that I was giving you. So with that setting, I can get that condition to be true. The last condition tells me that the MW plus diagonal nu has to be positive semi-definite. So then that of course means that all eigenvalues have to be non-negative. But unfortunately, that doesn't necessarily mean that the solution will be unique. So let me give you a very simple counterexample so that you will have a good intuition of what I mean by that. So imagine I gave you an idea of how to set nu, how to set Z, how to set the capital Z matrix, but imagine I change that a little bit. So imagine the true C star has 2 1s and 3 minus 1s. The only reason why I'm doing that is because I want 1 less 1 with respect to the minus 1. So any odd number of plus 1s, minus 1s, where I have an extra minus 1 will work similarly. So then notice here that I'm adding an extra 1. So when I add an extra 1, I have 3 1s and 3 minus 1s. So if I multiply this with a vector of all 1s, in the inner product, I will get 0. So that means that the vector of 1 followed by C star is orthogonal to a vector of 1s. Now imagine I take the capital Z matrix of the algorithm to be 1 1 transpose, a vector of 1's vector of 1 transpose. I can set the nu equal to the diagonal of MW 1 1 transpose, and everything that I told you so far will be true. So primal feasibility will be fulfilled. The stationarity plus complementary slackness will be fulfilled. So this will be equal to 0. And the same things that I told you about the 0 eigenvector and so will hold. So that means that not only what I told you before will be an optimal solution, a vector of all 1s will also be an optimal solution. So we don't have the uniqueness, right? So how do we solve the issue of uniqueness? So the long story short is that we know that this matrix MW plus diagonal nu has one eigenvalue being 0. And we know that what is the eigenvector associated to that, the one followed by the vector C star. We need to make every other eigenvalue to be strictly positive. So the second minimum eigenvalue of the matrix MW minus diagonal MW C star, that's because I replace the nu here to this definition there. So the second minimum eigenvalue has to be strictly positive. If that is true, then the Z star, one Z star, one Z star transpose, that's a unique optimal solution. And then we also recover the correct support. So this is, in short, to answer the first question, what the framework gave us. So the framework gave us these three conditions that we need to now show by using concentration inequalities. And for this, we will use, currently we are using subgaussianity and some mutual incoherence conditions for showing those three things. Of course, these are probabilistic events, and they depend on the random variable x, which is for n samples and the features, and the noise that we remember we have one scalar for each of the samples. And by solving these concentration inequalities is how we find what is the sufficient number of samples when n is greater than the size of the support to the power 3 times the logarithm of the dimension. Then with high probability, we can say that the method will recover the correct solution. And this is just some results that we found experimentally. So let me focus on the second chart that actually overlap nicely. So here, for instance, in the first one, we put the number of samples in the x-axis, and then the empirical probability of how well we are recovering the support of the vector W for three different sizes of problems, 100, 200, 500. If you control the x-axis to be in order of log D, then the three curves will overlap, showing that the rate that we are recovering actually happens in practice. We did the same with respect to the recovery of the labels C star for each of the samples. And you can do that by just inspecting the first row and first column of the matrix capital Z. You can get the labels from there because that gets multiplied by a 1 if you remember the rank 1 matrix. And if you overlap again by the correct log D kind of
I have a
dependence.
question.
Yes, tell me please.
So I'm just checking whether I understand correctly. So you're saying basically that you have this list of conditions that you can prove they hold with high probability using some concentration inequalities. And then you're saying if those conditions hold, then the invex optimization problem has a unique solution. And because it has a unique solution, this solution must also be a solution to the original optimization problem before the invex relaxation. So is that right, Rachel?
Yeah, no, it's a mix of two things, right? So remember that the way I was setting the C star, I was setting C star to the true values that generated the data, and the way I'm setting, for instance, in the way I was setting the zeros in the support, I was using here I not in the support of W star. So on purpose, I'm making these conditions to actually depend on the true values of W star and Z star that generated the data. And so it is a mix of using the C star and the W star in those conditions, as well as the uniqueness, right? Because I want this one C star transpose, for instance, to be the only matrix that will appear in that solution. Because maybe if I wouldn't control for uniqueness, I would not be guaranteeing that this is the only solution of that problem, the one C star transpose. That's a great question. And then the last thing we tested is what happens if I don't have the good knowledge of the gamma, right? And this is just tested experimentally. Like if I have a gamma, the true gamma is 2, but then I test with 1.5 or 2.5, experimentally things don't change too much. The particular algorithm that we were using here is actually an alternate optimization algorithm. So we actually, if you have alternate, then you fix W, you solve for Z, you fix C, you solve for W. We actually show also the conditions under which, because remember, you have two problems, right? Fixing W, solving for C, fixing C, solving for W. That means that if you have two problems, you have two KKT conditions. But what happens is that after some iterations, the two list of KKT conditions will be equivalent to the KKT conditions of the invex optimization problem. So then we can have a way to guarantee that optimization problem reach the optimal solution once the list of the two alternate optimization problems converge to the same. Then what I want to mention briefly is also we applied the same thing for many other problems, actually. So this is perhaps the furthest, the most recent work, but we have applied this to a structure prediction, and this is a max-cut type of problem. So here the problem is we want to figure out the node labels based on the information on edges, and the edges are generated in a noisy way. A very simple model for that was proposed a long time ago. Like the noisy model for edges would be, there is a true setting of the node labels, and then the edge is nothing else than the multiplication of the nodes intervening in that edge. And then you flip a coin with some small probability. You flip the +1 -1 edges, right? So for instance, here. +1 times +1 should be a +1, but here you can see a flipped edge. +1 +1 is a +1, but with a small probability that switched to a -1. And the problem here is, can you guess the node labels? Although there is noise in the edge labels that I gave you, can you guess the true values of the node labels in the problems? And this is very related to the max-cut problem. But we included many other things in the different papers that we have published. So we added issues of fairness. We added some of the squares type of solutions for this, not only the semi-definite programming, but also some of the Sparse relaxation. We have also analyzed latent variables in another paper in which the weight of this or the value of this edge label might depend on features for a node, features for another node, and the distance between the features in that feature space. So that's a little more complicated model. Here, this problem also has the second minimum eigenvalue greater than 0, and you notice that this problem has a graph. And as I mentioned before, even in the fair regression and clustering, you can also add extra conditions, and those extra conditions relate to algebraic connectivity of graphs at the end. So there are things about Fiedler vectors, Shiger constants, kind of factors explaining when do you get a second minimum eigenvalue greater than 0. In these problems as well. Other problems that we have worked on is in community detection. We have expanded these type of solutions for not only graphs where you look at the edges, but also hypergraphs where you look at hyper edges or relationships between 4 nodes, 6 nodes, and so on and so forth. But those are more like tensor type of problems. So for these tensor or hypergraph type of problems, we don't use semi-definite programming. We go to cone programming. So we have to define primal cone, a dual cone, and then there is a cone programming related to these primal and dual cones. And then there are KKT conditions also with respect to these primal and dual cones. And that's also kind of a interesting type of results we had. One of the first things that we did with these convex relaxations was to tackle problems of Bayesian networks, right? So that's the typical problem in machine learning in which you get data and you want to figure out a directed acyclic graph that best explain the data. So here what we did is a sequence of optimization problems. The idea is to figure out first the terminal node. So you can see here, for instance, the terminal node would be creditworthiness, but after you remove that layer, you can start removing the next terminal nodes after removing that. And if you recover all the layers of the Bayesian network, you can then just do a regression of the last layer or any layer based on the previous layer, and then you can recover the graph. This problem and all the problems that I showed you before are also worst case NP-hard. This one is related to the maximum weight directed acyclic graph problem, which is NP-hard and also NP-hard to approximate. But if you assume this generative model, you can also get an algorithm that recovers the correct Bayesian network or the Bayesian network that generated the data. The last one maybe I want to mention is work on graphical games. Here the idea is almost similar. Like you have a graphical game, and then players start following strategies. And then let's say in this case, you have the Congress, and let's say the strategy of every player or the best response of every player depends on in-neighbors. And then you are recording the votes that all of these congressmen are, all of these senators are doing in the Congress. And then the idea is, can you figure out the shape of the graph, like the nodes and the in-neighbors where they did the best responses that generated the data at hand, right? And then the answer is yes, we can do it. Even without observing the payoffs, without observing the utilities that they get, we can actually recover and figure out the graph of the neighbors of who is influencing who in these graphical games. We also have some several results for other more recent issues such as meta learning and so that also depends on Karushka and Tucker conditions. But I confess I didn't have the time for putting it in the presentation. And I think that's all I had for today. Thank you.
Thank you for this amazing talk. And is there any question from the audience? So again, thanks a lot. It was a great talk. And
yeah, thank you.
Yeah.
Thank you for giving me the opportunity. I really appreciate it.
Yeah, I enjoyed it a lot. Thank you. And we'll see you all next week face to face. So
take care.
Thank you again.
Yeah, take care.
Bye.
Nice meeting you.
See you.
Thank you. Bye-bye.
Bye.
Thank you. Bye.
Thank you. Bye-bye.